So exciting mix of aircraft that we're going to hear about. And we are going to start with Rob Bulaga, who is president of Trek Aerospace. Rob has been coming to CAFE Electric Aircraft Symposium since 2013. He has over 40 years experience in the aerospace industry as a designer and aerodynamicist. He's worked on a myriad of projects ranging from human-powered vehicles to hypersonic aircraft. He developed the CFD model used to design Trek Aerospace's ducted propellers. Besides designing Trek's various aircraft, he's also been the test pilot. An avid pilot, Rob's a longtime member of EAA and has served as president of his local EAA chapter. Rob and his team are competing in the GoFly Challenge with their FlyKart 2, which has been one of the winners in both Phase 1 and Phase 2 of that challenge. Please welcome Rob.
Well, thank you all. You'll have to put up with me and put up with some technology stuff now. The picture you're seeing there is our entry into the GoFly competition. We call it FlyKart 2. I'll give you a little background before I go into more details here. Trek's been around for 20 years designing and building ducted propellers for ourselves and for other companies. When the recession hit back in 2007, we stopped all internal projects and concentrated just on stuff that was going to bring money into the company to keep us afloat. We've ended up consulting on a few dozen different programs. Unfortunately, as many of you are aware, aviation startups fold just as quickly as they start up. So we've supported a lot of companies that have gone nowhere. A few years ago, we got tired of seeing our product never getting the light of day. So we decided to build a small project to demonstrate our technology. At the time, everybody was building flying cars, it seemed like, and we knew that we could not build a flying car. We're too small a company, and it was too hard. But we could build something smaller that would be a flying go-kart. So that's how the word FlyKart came about. It's supposed to be just something fun. Now we'll see how the clicker works here. That was the right one. There we go. That was our FlyKart 1. We built it in 2016. The goal for that was to build something that could fit in a one-car garage, cost as a kit under $20,000, and be able to be assembled by somebody in a weekend. We built the one that you see there. It's 6.5 feet in diameter, weighs 225 pounds, will carry a 175-pound person for about 20 minutes. Let's see, I got numbers here too, just because I always try to forget the numbers. That cost less than $15,000 in parts and took us about a month to assemble after we finished designing it. We did our first flights, say 3 years ago in 2016. And after that, we sent it with our partner in Australia so that they could test it there, because the flying regulations are a little more lax in Australia. They've done very little with it since they've had it. They've been busy with other projects. So it's kind of a disappointment to us. But because of this, when the GoFly contest came out, their requirements were so close to what we were already doing that we knew we had to compete in GoFly. So I got to point it there. Okay. GoFly, the goal of GoFly is to foster individual flight, as you'll be able to read that there. Essentially what they want to do is make something that anyone can fly anytime they want to. Their goal is, instead of looking at the sky and seeing an airplane and saying, oh, look at that plane, you're going to look up and say, oh, look at that person. Now, actually, Gwen, who created the GoFly and convinced Boeing to contribute the money to it, I think her real goal is to just put on Superman's cape and fly. I mean, she wants to fly from her home in Connecticut, land on the street in Manhattan, fold up whatever she's flying in, tuck it under her arm, and go up to her office. They're not going to get there, obviously, with today's technology, but they did start the project and ended up offering 3 levels of prizes, 3 phases. In phase 1, they had 10 $20,000 prizes that they handed out, and it was based on just a paper design, submit a report, independent people looked at it, judged it. Trek Aerospace and our FlyKart 2 was one of the 10 winners. Just bear with me here because I worked so many years on secret projects that my mind is trained to forget numbers. But so on the phase 1, they had over 800 teams enter, and they picked 10 winners out of that. In phase 2, they gave out 5 prizes of $50,000 each. We were also one of those winners. In phase 2, you had to update your report, but then you also had to fly a vehicle. Now, it could be a subscale vehicle. We were flying our full-size vehicle. Of the 5 winners, 2 of us were, and you'll see who the 5 are in a little bit. Then the prizes for phase 3, and then phase 2 ended just a couple months ago. Phase 3 will be a final fly-off. That's where all the big money is. There's $1 million for the people that win the big phase 3. There's scaling, I'll show you that in a minute here. There's also a $250,000 prize for the smallest vehicle, $250,000 for the quietest vehicle, and $250,000, or is it, I should look at that number, $100,000, sorry, for the most disruptive to technology. Now, smallest, I understand. You can measure that. Quietest, you can measure. Most disruptive, to me, that's like saying who landed the best, triple axle. That's going to be a very qualitative judgment. I do want to point out that all these prizes, it's not free to compete in GoFly. In phase 1, there was a $500 entry fee. That was essentially just to cut out a lot of the tire kickers. They had still 800 teams register for that, so that's $400,000 that they collected to support phase 1. When we got to phase 2, they got a little more serious. You had to give them 8% of your company. And now the GoFly people own 8% of everybody who competed. Well, they had 800 teams in the first phase. They only had 31 compete in the second phase. You did not have to win or compete in the first phase to compete in the second. You don't have to have competed anywhere now, and you can still join in for number 3. But they're still going to want the 8%. In our case, because we were a company that had been around for 20 years, we weren't going to give them 8% of our company. So we created another company, which is Trek Aerospace FK2 for FlyKart 2, and they own 8% of that. We get to keep all our intellectual property, but they also get to share in it. So it's not all just one-sided, though. They supply mentors, they supply discounts to some of the suppliers, they give us a lot of publicity, so we get something for that 8%. Somewhere there. Okay, the scoring for the fly-off. There are 3 things that count for the scoring. That's size, noise, and speed. On size, you have to be less than 8.5 feet in the longest dimension that you can measure on the vehicle. For every foot you're less than 8.5 feet, you get 1 point. For noise, they want you to be 87 decibels at 50 feet during takeoff and landing. For every 4 decibels you're quieter than 87, you get 1 point. Speed, they've set up a course, and you have to average 30 knots on the course. If you're less than 30 knots, if you're more than 87 decibels, more than 8.5 feet, you're disqualified. But the speed score, which is the third graph there, you notice that's not a linear score. So the elbow to it's probably in the 60 to 70 knot range. If you could fly Mach 2, you would get 1 point, the same as 4 decibels on quieter, or 1 foot on size. So obviously, size and quiet are the things to go for. Now, and because it's size and quiet, that's why we're here in an electric vehicle, because, that lets us get quiet. Now, the other, besides these main scoring points, and that's what's going to win you the $1 million, but they have many compliancy rules. There we go. So you see a big long list there. The sight lines, they want the open air experience. So when you're sitting in the machine, that 90-degree cone of your visibility out front, they don't want any of the vehicle visible in that. If you can see any of the anything visible, you're no longer compliant. You can't compete. So that means, like, if you were riding a bicycle and you could see, that front wheel would be in your view, so that couldn't be there. Ground transport, they want this so that one person can move it around, either push less than 50 pounds or lift less than 80 pounds to move it around. The takeoff and landing envelope, it doesn't have to be vertical takeoff, but they've created a takeoff concept where it's a 30-foot diameter circle with a 12-foot wall. So you have to be able to climb out of that cylinder. And at 30 feet, if you're an 8.5 vehicle, okay, you've got another 20 feet still that you could roll forward, but it's not a whole lot. The flight course that they've set up, or will be setting up, is 2 pylons, half a mile apart. You have to do 6 laps around them. So it's a total of 6 miles that you have to fly in that 20 minutes. 20 minutes or less. Well, actually, it's 12 minutes or less to average 30 miles an hour. At the end of the flight course, you have to be able to do a touch and go within that takeoff and landing envelope. So you got to be able to do a vertical takeoff and landing, or near vertical. Endurance, they want 20 minutes of flying time with 10 minutes of reserves after that. And you have to be able to do the vertical landing at the end of that 10-minute reserve, too. Harsh operating conditions. The pilot can never be exposed to more than 5 Gs. I think the only way any of these vehicles would be able to pull that is on landing, if you had a really hard landing. Operator weight, you have to design for a 200-pound person. And you don't have to fly the contest with a manned person. You can use a dummy, but it has to be still 200 pounds. And if you don't weigh 200 pounds, they'll ballast you up to it. Now remember, our FlyKart 1 was designed for a 175-pound person. That's why we couldn't just enter that in the contest. Airworthiness, it has to meet all FAA regulations and have an airworthiness certificate. In our case, we're going to be under Part 103, which makes life a lot easier. It has to be a single unit. There can't be any parts that detach after you take off. Energy sources have to be commonly available. Essentially, they mean electric or gas. I suppose if you could power it with soap bubbles, they think that was great, but nothing out of the ordinary. And then reusability. Between flights, they want it that all you have to do is refuel it. You don't have to replace any parts. I'll get this right here. So for us, there's 5 technologies that really make this possible as far as we're concerned. Structurally, what you're seeing on the left side there is the airframe for FlyKart 1. It's just aluminum tube, pop riveted together. That weighed 18 pounds. It cost about $350 in parts. We're on FlyKart 2, we're changing to carbon rectangular tubes. With the rectangular tubes, we can put the stiffness in the axis that we need it more, but the carbon also saves us weight. We ended up, instead of 18 pounds, the airframe for our FlyKart 2 is 9 pounds. Doesn't sound like a lot. It's 50% lighter. On a vehicle, though, where the empty weight, not counting the batteries, is only a little over 100 pounds, 9 pounds is a lot. Or for an electric vehicle, that's 9 pounds more battery we can carry, that becomes much more significant. The downside going with carbon is that that $350 to build the frame is now $2,100. So it's half the weight, but 6 times the cost. The next technology that really makes this possible is batteries. You know, this is an electric group. You know batteries are important. When we built our first electric vehicle, which is a small drone back in 2005, the LiPo batteries we were using on that were 140 watt-hours per kilogram. And they were costing us $1,600 per watt-hour, per kilowatt-hour. Today, off the shelf, we can buy the 18650 batteries. We're getting, those batteries are 240 watt-hours per kilogram, and they cost $700 per kilowatt-hour. So it's almost twice the power density for half the cost. That probably fits into that 4% or 6% per year that it's improving. Just looking there, again, I need to thank probably the automotive industry, but even more surprisingly was the vaping industry. The 18650s are what go into the vaping systems, and that's what's really driven down the cost of these things. So any of you that smoke, thank you. And any of you that don't, that's even better. Now, as an aerodynamicist, when I started working with electric aircraft, I had no concept for what all the intricacies were going to be on an electrical system. This is a chart showing how an 18650 battery, or basically any LiPo battery, works as it's being discharged. Along the bottom is the discharge capacity, up the side is how many volts you're getting out of the system. The bottom set of lines is how hot the battery gets as you're discharging it. That top line, the highest line there is 20 amps, which is about what we will be taking out of it during takeoff and landing. So you can see that the batteries get hot. You have to supply cooling air. That was fine. The top one is the one that bit me a few times as a prop designer, because a fully charged cell will give you just over 4 volts per cell. As you take energy out of it, you get less and less. When they tell you that a cell has 3.7 volts, that's about mid-range on there. At the end of your flight, when you're down to 80% charge has been used and 20's remaining, you're down between 3 and 3.2 volts per cell. That's the point where you've got to be able to still hover, you know, make your landings. So designing a prop, you know, that'll spin, you know, at whatever RPM based on what the kV of your motor is at 3.7 volts or above does you no good as you're trying to come in. You have to design for that landing voltage and then count on the fact that you're going to have excess during takeoffs. I say that one bit me for a couple of years. I kept, you know, because you design for what the battery manufacturer tells you that you got there. The next technology that has actually improved quite a bit too since back in 2005 when we started is the motors. And I actually learned at the cafe meetings here a lot about different motors. The motor pictured there is KDE, made in Oregon, but we've used Chinese motors, Czech motors, British motors. When we first started, we were getting, I should double check the numbers here, yeah, 3 to 4 kilowatts per kilogram on motors. Now, 15 years later, we're in the more 5 to 7 range. Back then, the motors were 85% efficient. Now, you're looking at normally 92 to 94% efficient. Of course, they tell you that's the efficiency. That's the efficiency at its best point. When you're actually running, we're using a 7 kilowatt motor. When you run it at that load, it's really about 77% efficient. And that's the other rub here. Go to the next chart here. You see on the performance of the motors, how many kilowatts you get versus time. And sure, the motor we have is rated at 7 kilowatts, but that's for like 10 seconds in a laboratory with perfect cooling. So for a 2-minute endurance, you're down, closer to 6 kilowatts. And for continuous operation, 90 minutes or so, you're down barely over 5 kilowatts. Now, and what it took me a while to figure out, again, being an aerodynamicist, is that when the motor's rated for 7 kilowatts, that's not what the prop sees. That's what the battery sees coming out of it. So it'd be like Rotax 912 saying, we're a 350 horsepower engine, because that's how much power is in the gasoline that we're burning. It does me no good, to say, oh, you got 7 kilowatts there, when really at 77%, they're only delivering 5 kilowatts to the prop. Now, it is important to my electrical guys that are designing, the cables, the controller, how many batteries we need on board. But as the prop designer, I really want to know what the power is at the shaft. So it took me a while to figure that one out. And then the KV of the motor. The KV is normally quoted by the manufacturer under no load. And under load, you're only going to get maybe 80% of that KV. So now the prop's not spinning as fast as I thought it was going to. Though now KDE, who makes our motor here, they give you the KV under load. So then you got to know, based on your engine company, which are you getting, under load or no load? And the best way to find that one out is actually to start testing your own stuff. So it's kind of been in a little uphill there. Now, luckily, or thankfully, Trek has been working with ducted props for over 20 years. We make probably the best ones in the world right now. I know it's bragging, I hate to do that. A free prop, which is the red line here, typically has a static thrust efficiency, or figure of merit, 45 to 55%. So what you're looking at there is disc loading versus how many pounds per kilowatt you can lift. The green line is if you just put a duct around a standard prop, that broken green line. And they run typically 55 to 65% efficient in static thrust. The props we build are between 80 and 85% efficient. So we're getting, well, down at the low end at about 5 pounds per square foot, the weight and the drag of the duct actually make it that you're better off with a free prop. Up at the high end, above 150 pounds per square foot, we just don't like to design there because it erodes the ground under the prop wash. As they were talking earlier, how the Harrier will dig holes. Well, that's about the same thing that happens here. You start really kicking up a lot of stuff. We actually prefer to design in the 20 to 40 pound per square foot range. And in that range, we make twice the thrust that a free prop makes for the same power. So that means we can use smaller motors or less batteries to do the same job. So even though we're using batteries that are 240 watt hours per kilogram, it's almost like we have batteries that are over 400 because of the improved efficiency we have of our prop system. So that's why we think we have a leg up on the GoFly competition. Our actual ducts, it's a combination, the shape of the duct and the propeller that's designed to fit in them. They have to be matched. And they have to be matched to the motor that you're using. If we put a different motor on there with a slightly different KV, that 85% drops really quickly down to 70%. I mean, it's easy to screw up a system. But yeah, we're real happy with that picture. There is our 16-inch duct. We've had 8 of those on FK1. We've got 10 of them on FK2. With the 7 kilowatt motor, we make a little over 50 pounds per duct lift. So we have a little over 500 pounds lift capability. The final technology that's making this possible, that's a picture of me flying our springtail aircraft back in 2005. That was under a DARPA contract, 2 ducted props, 42 inches, it's a lot like the Martin jetpack, but about 8 years ahead of them at that point. That vehicle with me on it weighed a little over 500 pounds. We had 800-pound lift capability with a 118 horsepower engine on board. That was an internal combustion. But the control system at that time, in 2005, you didn't have all the stability augmentation systems or autopilots that are available today. We worked with Stanford University, built a control system, and if they were referring earlier today to how planes were a handful to fly, well, this would be a handful and a half. And it was like standing on a giant beach ball in a swimming pool and trying to keep balance on it. It was constantly making small adjustments. Today, you buy an autopilot, kids are flying toy quads off their smartphones. And they're hands off, you stand there and watch them hover. I mean, if we'd had that back then, DARPA probably would have funded a follow-on project. But so the autopilot that we've got now on FlyKart 2, we bought it off the shelf, talked to the manufacturer, it'll handle the 10 ducts, and our first couple flights were exactly what we were expecting. We hadn't even adjusted the gains on it or anything yet, and it lifted up, it was stable. I mean, that just, since I'm the aerodynamicist, as far as I'm concerned, the electronics end is just something you plug on in and it works. Of course, my electronics guys tell me it's not quite that easy. So for GoFly, that's the 5 winners of Phase 2. That's right, I got the cheater down here. The 2 of them, you'll notice, the pilot stands up on. 2 of them in the upper left and right corners, you ride like a motorcycle. Ours, you sit in like a lounge chair or like a go-kart. 3 of us use ducted props, 2 use free props. The teams, I think the biggest team is the one that's in the upper right-hand corner from the Netherlands. They have 35 or 40 members to the team. It's a university. University of Texas down there, the Flying Egg is what I like to refer to it as. I think they have about 30 people in it. The Dragonair people, the ones standing in the middle, they're a team of 8 or 10. As far as ours, we're a team of 2. Plus we count on our local EAS chapter, lend hand, as we need it. But so we're more streamlined. They also look at us, though, as if we're the best funded. We haven't spent any more money on this than we've won so far. And it's to build the machine, which actually, the next one I can show you, that's the machine that we've been flying up till now. That's got about $45,000 worth of parts to it. FlyKart 1 used a lot of hobby parts, hobby motors out of China, hobby controllers. This is a little higher quality, which is good since I'm still going to be the test pilot on a lot of this. But so that's what we've been flying, and that one had the aluminum frame on it too. I said right now we have deconstructed that one. We are in the process of building FlyKart 2.1. And that leads me to that picture. That's what FlyKart 2.1 will look like. It's still the 10 ducts, but now they're fared in better into what looks like wings. They're not really wings. We've got a protection over the tops of the ducts, not so much to keep FOD out as to keep hands out. Let's see, what else the seat is a little fancier than what we've been flying, but also actually about half the weight. So right there, what we're looking at, we're 7.5 feet for the biggest dimension. So it's a foot bigger than FlyKart 1, but also a foot smaller than what we have to have. When we've been flying FlyKart 2, it's been running at 50 feet in the low 70s for decibels. So that's where we're going to get most of our points. I mean, that's going to be worth 3 to 4 points for us. Speed-wise, after hovering, our ducts actually, as you tilt forward, produce additional lift. so that we need less power in forward flight than we do in hovering flight. To hover this, we need about 48 kilowatts of power. To fly forward, we need 18. So it's a little less than half the power to fly forward. On that, we're carrying about 11 kilowatt hours of batteries, which will give us close to 40 minutes if we were just at cruise. With takeoff and landing, we're going to be down close to that 20 minutes plus 10 minutes reserve. So, I mean, with our props and that, I really think the other companies, either to fit in the size and that, they're going to be struggling. We actually had a company recently ask us, like a week ago, if we could help them out with ducted props, and we said, well, at this point, there's nothing we could deliver to you in time, because you have to be ready for your flight review in November, and then the final fly-off is going to be theoretically February 29th right now. Now, they did set the fly-off in the San Francisco Bay Area, supposedly so they can get a lot of publicity, but since we're located in Sacramento, that's like our backyard. It's a 2-hour drive for us. The guys from the Netherlands got to come halfway around the world. So we're appreciating that. Now, we have a booth set up in the Innovation Center this week. So if you have any additional questions after today, feel free to come by if you're still at AirVenture. I actually have to go to a meeting over there at 4 o'clock today. So if we get done in time, I can sit on the panel. But if we're not done in time, I'm going to be ducking out. And that's why we won't really do much with the questions there. That's actually me walking along, dragging a FlyKart 2 behind me at our airport where we've been testing. And I do want to throw out just one other thing while I'm here. The bottom plane in this poster is the XTI tri-fan. That's part of the reason that we're so far behind right now on our FlyKart. We built the prototype for that. It's a 2/3 scale. And that was supposed to actually be finished around Thanksgiving. We had lots of fun with the motors and the controllers that we weren't supposed to have. So we didn't actually deliver that to XTI until May. Now they've got that in Utah at an unmanned air facility there, and they're going to be starting hover testing with that probably this week or next week. But we spent, like I say, 6 months more on that we really had wanted to spend on FlyKart 2. So with that, I will exit stage right.